And welcome back. As we go ahead and dive into our next lesson with astronomy, we of course previously looked at the universe as it got very large, but we can of course take that scale and go the other way and look at the universe of the very small. Let's first off discuss this idea of the vast empty. Now, when we previously discussed the universe, we had talked about how it's extraordinarily large and empty. We have a lot of space between galaxies, for example. Now, space on average is about 100 times emptier than our galaxy. And yet, if you look at the galaxy itself, you can see it itself, by its own definition, mostly empty space. In fact, most of the universe is fantastically empty, whereas places that are dense, such as your own body, are tremendously rare. In fact, if you think about the only air we breathe, the air we breathe has about 10 to the power of 19 atoms in it per cubic centimeter. By comparison, the interstellar gas of the galaxy, the stuff that we see out in outer space, there's only about 1 atom in every cubic centimeter. So that's a huge contrast right there alone. Intergalactic space is filled so sparsely that to find a single atom, on average, we would have to search through 1 cubic meter of space. So just think about a meter, make that into a box, and you'll have only 1 atom that exists within that box. And so this empty space is quite terrifying, but it is also something that is also very fascinating. Even when we start looking at objects themselves, so let's just say we had, instead of that empty box with 1 atom in it, let's just say we had a box that was instead maybe a solid block of iron. Those are going to be mostly empty space. And if we take apart those items, such as that solid block of iron, and we take it apart piece by piece, and we keep going down and try and make it into smaller pieces, we'd eventually reach the tiny molecules from which it is formed. Now, molecules, of course, are the smallest particles in which any matter can be divided while still retaining its chemical properties. For example, if I were to say a molecule of water, or H2O, this is going to be 2 hydrogen atoms and 1 oxygen atom bonded together. That's the chemical composition for water. If I had something else, it would not be water anymore. And we, of course, talked about something else there. We talked about hydrogen and oxygen, and that's going to get us a little bit into the chemistry side of astronomy here when we start talking about elements. Because molecules, in turn, are built of atoms, which are the smallest particles of an element that can still be identified as part of that element. So, for example, an atom of gold is the smallest possible piece of gold. Now, there's nearly 100 different types of atoms or elements that exist within nature. Now, most of these elements are extremely rare, and only a handful really account for more than 99% of everything in which we come in contact with. In fact, if we look at Earth alone, the 4 elements that are the most common are hydrogen, carbon, nitrogen, and oxygen. If we look at this on a cosmic scale, well, you can see that hydrogen is still, again, the most abundant atom. So if we say, hey, you know what? If we look at the number of atoms per million hydrogen atoms, so if I had just hydrogen, and 1 million hydrogen atoms, of course it's going to be 1 in a million of them. But if I throw some helium in there, well, of that 1 million, only 80,000 of them would be helium. If I were to throw carbon in there, well, only 450 out of that million would be hydrogen. Nitrogen, 92, oxygen, 740, neon, 130, magnesium, 40, silicon, 37, sulfur, 19, iron, 32. Just, again, give you some idea of how abundant some of these things are found in the cosmos. Now, what if we were to be able to peer inside of an atom itself? What kind of mysteries could we find out about our universe? Well, all atoms consist of a centrally positively charged nucleus surrounded by negatively charged electrons. Now, the bulk of the matter in each atom is found in the nucleus, which consists of positive protons and electrically neutral neutrons that are tightly bound together in a very small space. Now, each element is defined by the number of protons in its atom. So, for example, an atom with 6 protons in its nucleus is always going to be called carbon. It does, as soon as you change it out of 6, it's going to be a different element. If you had 50 protons in there, it's going to be tin. So on and so forth. So the number of protons, neutrons doesn't matter, but the number of protons in there will determine which element it is. And going back to our conversation on distances, let's think about the space in an atom, and let's try and pretend we scale that down. How far apart would things be? Well, the distance from an atomic nucleus to its electrons is typically about 100,000 times the size of the nucleus itself. And this is the reason why we can say that even if something is solid, it is mostly empty space. For example, the typical atom is far emptier than our solar system from the sun all the way up to Neptune. The distance from the Earth to the sun, for example, is only 100 times the size of the sun. We're looking at 100,000 times. So this is quite a distance here. And this is just one of the reasons why atoms are not necessarily like miniature solar systems. Because if we think about a solar system, well, between the sun and Neptune, we have a bunch of stuff in between. We have a couple planets, we got some moons, we got some asteroids. But if we look at the atom, there's nothing there. It's literally just empty space. And that's going to kind of get to one of our last things to kind of really think about as we talk about the universe on a small scale, which is the fundamental forces of the universe itself. Now, physicists have discovered that everything that happens in the universe, whether you're going from the smallest atomic nucleus to the largest superclusters of the galaxies, these can be explained through the action of just 4 different kind of forces. The first one we were probably familiar with. It's gravity. You feel gravity every day when you, for example, you try to jump up and you come back to the center of the earth. Guess what? That center of the earth pulls you down, you hit the soil, you're not going any further. Electromagnetism. This is also something that we are probably very familiar with. You've ever done anything with a magnet, for example? Guess what? That's electromagnetism. You ever work with electricity? Electromagnetism. And then we have strong and weak nuclear forces, which is a topic that is beyond, what you might understand for the scope of this class, but know that this is, again, the other 2 forces that are in play. And of course, gravity and electromagnetism were the first discovered. Strong and weak nuclear forces were a much more recent discovery, but it's still a very important part of how everything interacts in the universe.